Okay, welcome everybody. My name is Michael Demkovic, and I am very happy to welcome all of you back to our SSDDS summer school on dynamic deformation of solids. Today, we are very happy to embark on lecture number 3, which will be given by Bill Anderson from Los Alamos National Laboratory. So, by way of reminder, if you're signing on and you have not yet muted yourself, please mute yourself upon sign on. So, this is being recorded. We want to make sure that the recording, minimizes noise for everybody. If you have, if you do not consent to being recorded, then my suggestion is sign off, watch the recorded video once it is posted online. Another alternative is just to keep yourself muted and your camera off while you're on this teleconference. So, Bill Anderson will be giving today's lecture. He will also be giving next lecture. So, but let's just start with who he is. He is currently a technical staff member at Los Alamos National Laboratory. He's been there since 1998, 22 years. He got his PhD at Caltech in 1990, and after that, had an extended stint at Caltech, first as a postdoc and then as a research faculty member at Caltech, followed by a brief term in academia as an assistant professor before joining Los Alamos. He is an APS fellow and has interests in shock compression of condensed matter. Before I hand it off to Bill to take it away for today, I just wanted to mention that all of these lectures are being recorded, and I post the recording because I've had a lot of questions about this. I post these recordings as soon as I receive them, but the way webex works for some reason, it records to the cloud and then sends me an email when the recording is ready. So it's not always ready immediately. So I ask you to bear with me, please, while I wait for the video to show up. So with that, I'll hand it over to Bill. Bill.
Okay, thank you. Make sure, can everybody hear me?
Yep, I can hear you.
Okay.
Are you able to share your screen?
I believe so. There we go. Okay, so today I'm going to be...
Bill, I cannot see your screen. Are you showing slides?
I am showing slides now. Let me try and share again.
Okay. We can only see your cursor, and if you could move a little closer to the microphone, you come like a very distant phone call you're coming to us. I get Michael much better than I can hear you.
Okay, let's see if I can take care of that. Can you hear me now?
Yes, and you can only see your cursor in front of the black screen.
Okay, let me try again. Okay. Says sharing start. Recording. So share content. Okay. Can you see this now?
Yes.
Okay.
You don't see it in presenter mode. If you can do that, that'd be good.
Excuse me?
Well, there's presenter mode. You can make it a little bigger.
Yeah.
That'd be nice.
Okay.
Sorry.
Okay. Hopefully you can see my cursor. I've noticed that in some of the lectures, the cursor is a bit hard to spot. So I've tried to make it as large as I could and easy to see when I move it. So today I'm going to be talking about stress waves, and next week I'll be talking about, in particular, shock waves. But there are some differences between stress waves the way I'll be talking about them today and tomorrow. Of course, since stress waves are stress waves, we need to understand stress and strain first, and then I'll talk about stress waves and what those waves do when they hit interfaces or boundaries. And finally, I'll give a little preview of some of next week and some problems. I should point out that this lecture is going to be a bit more mathematically dense than the first two lectures. There's not really a good way to get past that, but I'll try and explain things for those who may not have all the apparatus available. And a few other notes to start off. When we get into talking about high pressure work and dynamic deformation, there are a wide range of academic specialties that make use of apparatus in that field, and they all tend to use different symbols for the same things, or in some cases they recycle symbols. And my warning is just to make sure you understand what a person is presenting when you see some symbol. And finally, as Lauren Benedict noted last week, there are units that are sort of special to the high pressure business. I'm not going to be really discussing things that have units today in particular. I'm not going to be presenting numbers, but just be aware that there are issues and don't get confused when you go reading the literature. Okay, so in the previous lecture, Lauren talked about thermodynamics and he talked about the energetics associated with volume strain and also the addition of heat in relation to the equation of state of a material. Equation of state usually involves pressure and volume compression. Those are specialized bits of the more general framework of stress and strain. The equation of state, as presented, generally ignores deviatoric stresses, and I think that some of the questions last week touched on that fact. This week, we will be discussing things that are dependent on the equation of state, but we go past that. So let's begin with stress. This is going to look very familiar to many people who've had a solid mechanics course, but in order to make sure that everyone ends up on the same page in terms of both the symbols and understanding what I'm talking about, I'm going to discuss stress and strain a bit first before talking about waves. So imagine if you were to take a little cube of material and it's got surfaces, and those surfaces have the normals to those surfaces are 3 orthogonal directions. Lots of times lecturers will present them as X, Y, and Z because when we get into talking about the matrices or the tensors that go along with these directions, generally they use numerical subscripts. I'm going to stick with the numerical subscript. So what would be X is going to be X sub 1. Y would be X sub 2, and Z would be X sub 3. Now, if you take a force, keep in mind a force is a vector. It's got both direction and a magnitude, and you apply it to that surface, you end up with a stress. The stress is the force divided by the surface area. And because that force can be in any random direction, it typically isn't going to be aligned with one of our 3 orthogonal axes. And therefore, we can break that vector down into three components that are orthogonal in the x1, x2, and x3 directions. If you do that for each of these 6 faces of the cube, 2 faces, there are 2 faces each that have normals in each of the 3 directions, you get a 3 by 3 matrix. You get 9 unique stress components. The convention here is that the first component, or the first subscript, is going to be the direction in which the stress component is acting. The second one is the orientation of the plane that that stress component is acting on. Usually, as I just said, these components are usually presented as a 3 by 3 matrix called the stress tensor. For the purposes of those who aren't really up to speed on tensors and on matrices, it's basically a grid where the first row is things in the x direction, the second row is things in the y direction, the third row is forces components in the z direction. Now, I'm going to go ahead and say, really there are only 6 independent stresses because this matrix turns out to be symmetric. Therefore, the 3-1 stress component is the same as the 1-3. 2-1, the same as 1-2. 3-2, the same as 2-3. So that makes life a little bit easier. Now, if you take us, as you was noted, and the whole purpose of what we are talking about in this course, we're talking about deformation of materials. I, in particular, am talking about the deformation of materials and result from stresses, and the deformation is called strain. So now, if we take our little cube of material and we pick some point inside that cube, and it has, you know, some position in our coordinate system, and we very slightly displace it. We displace it with by a certain amount u1 in the x1 direction, u2 in the x2 direction, and so forth, and it ends up in a different place. Now, if we take a point that's very close to that point, offset by delta x's in the 1, 2, and 3 position, directions, and we displace it, it will be displaced maybe by a very slightly different amount, so that in the x1 direction, instead of being displaced by u1, it's displaced by u1 plus delta u1. If we shrink these very small differences down to the limit, then we get differentials. And we can write these deltas as the partial derivatives. And as is common in this business, I'm not going to put these things inside parentheses with all the stuff that's constant outside. I'm just going to say it's the partial derivative of the displacement in the one direction with respect to the position in the one direction, plus the partial in the one direction with respect to position in the two direction, and so forth. We can get the differential values of these three differences in displacement. So if you take all of these together, again, you have 9 derivatives right here of displacement with respect to position. Those define the strain, which is the distortion. They also define rotation and displacement. What we're going to care about, of course, is the distortion of the material. The distortion comes in 2 different flavors. first is dilatation, where we're changing, say, the length of our little block or whatever in one direction, or a second direction, or a third, or all three. The second is shear, where we aren't actually changing length, but we are sort of stretching the thing and causing it to deform sideways. Now, one of the things you will notice if you, say, go to the classic book on stress waves by Kolsky, he has a different definition for epsilon 2,3, which is a shear strain. He has it as being the sum of these without being divided by 2. I've divided by 2 because that's how you get this into the tensor form. Again, it's a matrix. The last row here is rotation. So if you were to rotate the whole block, that's what this last row describes. And I don't show displacement because that actually is related to the rotation by a vector quantity called the curl. We aren't going to worry about that in this talk. So, as I pointed out, these things can go into a tensor. It looks very much like the stress tensor. The subscripts have the same meaning, almost the same meaning, because now we're talking about shears. But again, we're still working on the plane that is being, the force is being applied to, or in this case, the deformation is occurring in, is going to be the second subscript, and the direction of that deformation is going to be the first subscript. Okay, strain is a differential quantity, and this has some consequences when the strain's not small. For most of this talk, we're going to think about situations where the strain is very small. Now, if we look in the real world, though, we deal with macroscopic objects. And so when you go read a paper where somebody has actually performed an experiment and presented a strain that has occurred in their sample, they're talking about something that's big enough to be measurable. And so just a very brief divergence from the main part of this talk is that
I would just remind, please mute yourself. If you don't come in muted, please mute yourself.
If a person presents the strain, then you might see it presented in one of two different ways. The first way is sort of a simple thing. So let's just take longitudinal strain, so dilatation in the one direction. So that would be epsilon sub 1, 1. So that's basically a change in length in the x direction. Let's say whatever our sample was started off with a length Lx0, Lx0, and it undergoes some change of length delta Lx to a new value that is just the sum of that change plus the original. The simple way to express this is using something called the engineering strain, which is where you just take that change in length and divide it by the original length. The issue is, because strain is defined as a differential or a derivative quantity, the better way to express it is as an integral, which we call the true strain. So this is what that integral would look like, and the quantity ends up being the natural logarithm of the new length divided by the old length. And if you take very, very small strains, these two give the same numerical answer, which is why often you will see the two used almost interchangeably in some cases. The other thing I wanted to point out is that linear displacement of an object we aren't talking about. Rotation we aren't going to talk about, but this is just showing this is the displacement vector, and here's the curl quantity. It's related to the rotation. And that's all I'm going to say about it. We don't really need to worry about this for the purposes of this lecture. Now, in high school physics or freshman physics, you probably dealt with problems where you took a spring and you stretched it or you compressed it, and you found that the force of that spring was equal to some constant called the spring constant times how much that spring was compressed or stretched. That is called Hooke's law. Now, in solid mechanics, continuum mechanics, we have the same sort of issue where we can take stresses and strains and relate them by ratios. If those quantities are sufficiently small, then whatever that ratio is can be considered to be a constant. And we call that an elastic constant. And when these elastic constants are constant, then we term that particular situation linear elasticity. Now, in linear elasticity, we take our two 3x3 matrices and we relate them. So each component of the stress tensor has a relationship to each of the 9 components of the strain tensor. And when you take that,
Bill, do you mind if I stop you for just 1 second? We're getting a lot of requests to ask you to click on the display settings menu on top of your screen and switch the swap presenter view and slideshow. So if you go back into your presenter view, so just start up the presentation. Just so no need to exit the presentation. Just start up the presentation as you do.
So in PowerPoint.
Yeah, in PowerPoint. Just
okay. Okay.
So just start the slideshow. You can press it on the bottom right. There's a slides. Yeah, or in the menu. That's fine. Either way.
Oops. Let me go over here. Okay. And what would you like?
So just enter the slideshow view. Yeah, press that.
Slideshow view. Okay. Yeah. Oops.
Yep. And you see on the top there should be a menu that says display settings.
Oops. Yes, there we go.
Okay, press that and swap.
Okay. Okay. All right.
Thank you. Perfect.
Okay, so now I can't get my, can you see my cursor still?
Yes, we can.
Okay, because I'm using a double screen and it's not showing up on one of my screens. Okay, so let me get things out of the way here. Okay, so as I was pointing out, the 9 components of stress are related to the 9 components of strain by 86, and that's a lot. So I have the, oh my goodness, what am I doing here? 86 elastic constants. So you've got the normal way is you take the sigma sub ij, and it's related to each of the epsilons and KLs by a C sub ij KL. Fortunately, the fact that both the both the strain tensor and the stress tensor are symmetric, it turns out that a lot of redundancy exists in these elastic constants, so that there's actually only 21 independent values. That makes life a bit easier. And the convention is not to present these elastic constants with all 4 subscripts, but to condense those subscripts into 6 independent IJ and LK, or KL, I should have said, pairs in what's called Voigt notation, so that for the remainder of what I present, 1, 1, so say sigma ij is sigma 1, 1, that's going to correspond to the first subscript on C being just 1. 2, 2 would be 2, 3, 3 is 3. Now, counterintuitively, 2, 3 is 4 rather than, say, 1, 2. But the reason for that has to do with the way that matrices work when you are doing that. So just be aware of the fact that 2, 3 is 4, 1, 3 is 5, and 1, 2 is 6. So for instance, if we take our symmetry in epsilon and we look at how sigma 1, 1 behaves, that's going to be sigma C1, 1 times epsilon 1, 1 plus C2, 2 times epsilon 2, 2 plus C1, 3 times epsilon 3, 3 plus 2 C4, 4 epsilon 2, 3, and so forth. The reason for these factors of 2 is that these cover both sides of that symmetric matrix, of these symmetric matrices. So the longitudinal or dilatational parts of these have to do with just singles, whereas the ones that take the off-diagonal parts of those matrices, those you double to account for both the upper triangular and lower triangular parts of the matrix. Now, 21 constants is still a lot. People start having problems when they get to that many independent things describing a single material and just describing how that material reacts to stress that's applied to it, or how the stress depends on the strain of the material. Fortunately, symmetry can come to the rescue and further reduce the number of non-zero or independent elastic constants. One other thing I should point out is that often, you know, in our everyday lives, we don't think about stress per se, we think about pressure. Now, the pressure is actually related to those dilatational components of the stress. It's the average of the dilatational components in the 3 different directions. There's a negative here, and the negative is here because in engineering and material strength work, strength of materials, the convention is that stress is positive when you're stretching the material or when you're pulling on it. And so it's strain. And that compressing a material, the stress and strain are negative. we're going to next week change those definitions, but I decided for this week that we will stick with the convention where people normally work in these sorts of things. The differences between these individual components and the pressure, keeping in mind that the pressure is the negative of these, is called the deviatoric stress. So the deviatoric stress in the I direction is sigma II plus P. If those stresses all happen to be the same, then they are just equal. Each one is equal to the negative of the pressure. And we call that particular situation the hydrostatic condition. All the deviators, that's what we sometimes call these, all the deviators are zero. Notice that an analogous set of quantities can be defined for strain, but since the material might be anisotropic, and we'll talk about that shortly, the definitions are going to be somewhat different. Most importantly, though, we will be dealing with something called the volume strain, and for shorthand, I'm going to call it delta. And delta is just the sum of the dilatational strains. Now, I said symmetry helps. In some cases, symmetry helps a lot. So if you have some material where there is no special symmetry, so in crystallography, we'd be talking about a triclinic crystal, where none of the crystallographic axes are orthogonal to each other, where none of the unit cell lengths are the same. So there aren't any repeated properties from one direction to another direction. You're just stuck with this thing not having special symmetry. In that case, you're stuck with all 21 elastic constants in order to completely describe the material. Fortunately, most materials are not that asymmetric. Most materials that we deal with have inherent symmetries that result in some of the elements of the elastic constant matrix, which if you were to go in and add it all up, it's a 6 by 6 matrix. That's 36 separate components. Of course, like I pointed out, it is symmetric, but it results in some of those elements vanishing or being redundant. In particular, there's a actually quite large class of materials that we call isotropic solids. Isotropic solids have properties that are independent of direction, and they only have two independent constants that we normally call Lemai's constants, and they can be expressed in terms of the elastic constant, C11, 13, 2, so forth and so on. You can see here, all 6 of these are equal to lambda. The 3 of these are equal to mu, and then lambda plus 2 mu actually equals these right here. And you might notice that these are the constants that correspond to dilatational strain in response to dilatational stress. Now, most crystalline materials are not isotropic inherently. The thing is, many engineering materials are polycrystalline, and quite often the orientations of the crystals or the grains in those polycrystalline materials are random. And when you have a situation like that, even though the underlying crystal symmetries are not isotropic, the material itself at the bulk scale is effectively isotropic. It's because you're averaging out the directionality of the different crystals in the material. Because isotropic solids are so important, and the concept of isotropy is going to be particularly important when we start talking about shock waves, I'm going to spend a fair amount of time talking about isotropic solids and waves in isotropic solids. Because notice that there were 12 elastic constants here from our full elastic constant matrix. All the rest are zero, identically. So let's rewrite our stress and strain relationships for an isotropic solid in terms of Lemay's constants. So stress 1,1, sigma 1,1 is now equal to the dilatational strain times lambda plus 2 times this mu constant times the longitudinal strain in the 1,1 direction, and so forth. You see the same relationships in the other two directions. And in the off diagonal parts, the shear stresses are related to the shear strains by 2 times this quantity mu. And again, I point out that the dilatational strain is just the sum, that should be a 3,3 there. It's just the sum of the dilatation of the individual dilatational strains in the 3 different directions. So this is the volume strain. And keep in mind that all these relationships are based on very small, ideally infinitesimal deformations. Now, let's take a particular special case of an isotropic solid under what we call uniaxial stress. So we're going to take a block of material and we're going to squeeze it with a stress that's applied in only one direction, along one of our principal axes. We're going to require the stresses on the sides to equal 0. Well, you know, if you take a marshmallow and you squeeze it with your fingers, it's going to bulge out. And so you're going to change the lateral dimension is going to increase as the linear dimension decreases. And it has those changes in dimension, the strains associated with those are going to have to satisfy this set of equations right here. Your stress in the the 1,1 component of stress is going to equal to this, and the other 2 dilatational components of stress are identically 0. So you have to make all the different strains work together to satisfy these 3 simultaneous equations. If you solve these, what you find is that the dilatational strain in the one direction, the x direction, if you will, has this relationship to the stress. The strains in the other 2 directions, now remember we're talking about an isotropic solid, so there's no particular difference between 2,2 and 3,3 in terms of material properties. They're going to be related to the stress in the 1,1 direction, or the 1 direction, by this ratio here, or the ratios of the strains is going to be given by this right here. So we have our 2 Lemay's constants that fully describe this situation. Now, it turns out that, these, while not really difficult, these particular equations have a lot of writing that goes along with them. So it's, for convenience sake, common to define 4 elastic constants for isotropic materials. One of them actually is an elastic constant that applies to all materials, but right now let's stick with isotropic materials in terms of Lemay's constants. The first is Young's modulus, which is this right here. Second is the bulk modulus, and we'll be talking about it a good deal more. Third is the shear modulus, and it turns out to be exactly the same as our quantity mu. And finally is something called the Poisson's ratio. And if you go and you look at what these ratios are, the Poisson's ratio is related to the differences in strain. Actually, those should be stresses. I'm sorry. I have made an error there. Those are stresses. Oh, I'm sorry. I'm getting ahead of myself. The Poisson's ratio deals with the ratio of the lateral expansion of the material, if you will, to the longitudinal contraction. And Young's modulus is just the ratio of the stress to the strain. The bulk modulus is best understood in hydrostatic stress, and it is the ratio of pressure to the volume strain. And it turns out bulk modulus has this definition regardless of the symmetry of the material. So even for materials that have no special symmetry, bulk modulus obeys this. It, in fact, is a thermodynamic derivative and is integral to almost all equations of state that people use. Now, there's a different condition called uniaxial strain. And in that situation, which is the normal situation when we're dealing with stress waves, you have some extended material. You've got a big chunk of material, and you're dealing with what's going on inside of that chunk of material, where if you would squeeze it in one direction, the problem is it's surrounded by more of the same material, so things can't get squished out the side. Therefore, the strains in the lateral direction are 0, and the strain in the longitudinal direction is non-zero. Well, now you have to simultaneously solve the equations that will give you that. So what you'll have in a situation like that is the longitudinal stress is going to be looking like that, and the lateral stress is equal to that. Notice that all the other strains, 2,2 and 3,3, are 0, so they don't enter in there. And in terms of our elastic constants that I said are a bit more convenient, the longitudinal stress is related to the longitudinal strain by this quantity here. Involves the bulk modulus and the shear modulus, and the stresses are related to the lateral stresses are related to the longitudinal stress by this ratio involving Poisson's ratio. Now, not all materials are isotropic. So let's talk briefly about the sort of next step up in asymmetry. There are materials that are called orthotropic solids. An orthotropic solid has 3 orthogonal planes of symmetry, but the properties may not be the same in those different directions. In increasing order of symmetry, those go, in crystal systems, we'd be talking about orthorhombic or tetragonal or isometric, also known as the cubic. Orthotropic solids, by their symmetry, have at most 9 independent elastic constants. And here they are. I'm not going to name them all. I'll just mention that, of course, a very large set of materials, for instance, lots of salts, lots of things, lots of metals are isometric. In other words, their symmetry is cubic. They have 3 fourfold rotational symmetry axes, and the properties along those different axes are the same. The thing to point out is that isometric does not necessarily mean isotropic. A commonly used isometric material in shockwave research is lithium fluoride, and lithium fluoride is far from isotropic. Now, in these isometric or cubic solids, because of the extra symmetry, again, some of these things are redundant. So the CIIs, if you will, are all equal. The first 3 are all equal, dealing with dilatational strain. These quantities are equal, and these quantities are equal. So there are really only 3 independent elastic constants in isometric solids. Now, some cubic materials, isometric materials, can be isotropic. And the deviation from isotropy is often quantified by what we call the anisotropy ratio. Here I write it as A. And it again is related to these more convenient elastic constants, or in terms of our original elastic constant matrix, it's these quantities right here. If A equals 1, the material is isotropic. And to the extent that A differs from 1, the material is anisotropic. Okay, why have we talked about this for a good fraction of an hour? Well, we've talked about it because stress is force, and strain, or the rate of change of strain, is velocity. And one leads to the other. And so now we're talking about the equations of motion, Newton's laws. So, for example, let's take a force acting in the x1 direction. That force, which we'll call F1, is these 3 things here times these 3 things here. Now, if we take Newton's second law, and we don't worry about things like gravity that sort of act equally on the whole thing, the force can be written in this way. Keep in mind that U is displacement, so the second time derivative, that's an acceleration. And so you've got a mass, you've got a density, this is mass density, times a volume, length times width times height, if you will. So there's a mass, and you've got an acceleration. Force is equal to mass times acceleration. F equals ma. So back to just freshman physics there. Now, we can rewrite this using these and say that the density times this acceleration is equal to these 3 spatial derivatives of stress in the one direction. And you can change these to correspond to displacement or strain in the x2 direction or the x3 direction. These results, this is Newton's laws, they don't care what the properties of the material are. The material has to obey these equations. But of course, if you're going to actually solve for numbers, you need to know, have numerical values for the material properties. So again, let's go back to our nice, simple isotropic material and think about motion in that x1 direction. So this is the way we could write this using Lemay's constants. And let us remember what the definitions of these strains are. If we combine these, we can write an equation that's a little bit more compact. It looks like this, where this is just a shorthand notation. It's a vector notation, but it's really just a shorthand for the second partial derivatives of whatever is after it, in this case, u sub 1, with respect to each of those three orthogonal directions in our coordinate system. And again, we can do the same equation with respect to the x2 and the x3 directions. These are equations of motion in what we would call an elastic isotropic body. Now, what happens if we have something that obeys these equations and we do the following? Let's take a block of this material and only on one surface, not on the opposite surface, so only on one surface. So now we're going to have an unbalanced situation. Only on one surface, we apply some time-varying force. Okay, because that stress is unbalanced, that's a net force, things are going to move. I mean, we accelerate the material. So the atoms at that surface are accelerated, they move, so that there is a corresponding time-varying strain. Now, there is actually a bit of a lag because force is acceleration, but the material will balance it. Keep in mind Newton's third law. The material is pushing back with that same force, and that pushback is related to the strain. So, but when these atoms move, okay, atoms sit in a potential well due to the other atoms in the material. Lauren Benedict pointed that out last week and showed diagrams. This lecture is a lot less, has a lot fewer graphics in it just because it's so long. But when those atoms move out of their positions, they change the potential wells for the atoms that are by them. And now those atoms feel a force and react. And so those atoms are moved, but there's a time lag there. There's time to react. Those atoms do the same thing to the atoms even further away from the surface, and so forth and so on. And so what you end up with is this disturbance in stress and strain that is moving away from that surface where we originally applied it. That is a wave. Now let's look at this wave in terms of those equations of motion that we had on the previous slides. Now, if we take all three of those equations of motion, so in the x1, x2, and x3 directions, we add them and we differentiate them with respect to x1, x2, and x3 and those three directions. So for instance, this one would be differentiated with respect to x1. we differentiate them, and we add them all together, you get something that looks like this. Here, remember, this is our volume strain. This is our volume strain. We've got Lemay's constants here. You may remember that this is what the stress looked like relative to the strain in the uniaxial strain condition. And for those of you who've done, a lot of electromagnetism work or dynamics work, you might recognize this as being the wave equation. A second derivative of some quantity with respect to time is equal to some constant of proportionality to the second derivative of that same quantity with respect to position. In that particular case, in this case right here, this is a wave equation where dilatation is moving through the medium with a velocity that's equal to this quantity right here. And you'll notice this right here. This is our stress again, and or our stress ratio to the strain. Here's our mass density, and it's a square root.
My phone dropped the fucking call. And then I tried to call this.
Please remember to mute yourself. Please remember to mute yourself.
I don't know how much Bill has to talk, but I have another WebEx.
Hello? Please remember to mute yourself. Okay.
Hold on a second. Okay. Okay. So, under normal circumstances, the material is self-constrained, as I pointed out earlier. It's the uniaxial strain condition. In that particular case, our volume strain is exactly equal to the strain, the 1-1 component of strain. A wave that does that is a longitudinal wave, because the motion of the atoms in the medium is in the same direction as the wave is moving. So, or along the same axis. In the favorite high school physics teacher's example, this would be a slinky. Imagine that each of the coils in the slinky is a layer of atoms. The atoms get compressed or stretched depending on the sense of stress in the material, and the wave is moving along the length of the slinky. And since it's a longitudinal wave, that's why I called the velocity C sub L. Now, because the lateral strains are zero, and the lateral derivatives, therefore, are zero, we can think that of the any particular localized portion of the wave to be planar. And so we can now write that wave equation to look like this. The general solution for that wave equation is going to look like this. Keep in mind that waves don't have to be sines or cosines or anything like that. There's a general solution that involves a spatial position plus the wave speed times a time position. And there are two possible solutions, one for waves propagating in the forward direction or the positive direction, and one for waves propagating in the negative direction. What you can see is, except for a constant offset and, of course, the scaling factor. Let me see here. Okay. for whatever reason, my cursor moved on me. Can you still see the cursor?
Not anymore.
Okay, let's see here. I'm not sure what I did. Let's go back. Okay, my cursor went away, so I'll have to try and make things clear enough as what I'm pointing at. The general solution has this form that is this f function plus a g function. They are not necessarily the same function, but the same functional form applies to the stress as to the displacement. So if we take the stress derivative with respect to position and we can relate that to the stress derivative with respect to time by just minus 1 over the sound speed, or the longitudinal wave speed in this case. We can integrate this in time to get an equation that looks like this: rho times the spatial times the time derivative of displacement, so that's a velocity, is equal to 1 over, or minus 1 over CL times sigma 1,1. That time derivative of position is actually the velocity of the material in the wave at that point. If you can rearrange this, you will see that the derivative, or that the stress in the wave is minus the density times the longitudinal wave speed times the speed of the material. We're going to see this same equation in a slightly different form next week. Now, what about the case where we force the volume strain to be 0? So there's no dilatation to speak of. Okay, if you do that, then you have these equations up at the top that relate velocities, or actually accelerations, in the U1 and the X1, 2, and 3 directions to the spatial derivatives of the velocities. Now, because of the way that the full equations of motion work, and because the material self-constrained, we can't have longitudinal strain. What we will get is another wave equation. These are all wave equations, but they have a different propagation velocity, equal to the shear modulus divided by the density square root of that quantity. Those are called shear waves. They're transverse waves. And what does that mean? Again, let's look at our slinky. Again, this is kind of an extreme example, of course, but the wave is moving along the length of the slinky, but the motions of the layers of atoms, or the coils of the slinky, are actually transverse, or orthogonal to the wave motion direction. We call that a transverse wave, or more commonly in some specialties, a shear wave. Now, imagine that a longitudinal wave carrying a longitudinal stress, sigma, in an isotropic medium. What are the stress deviators? Okay, in an unbounded medium, the stress deviators are essentially 1/3 of the total stress. In a bounded medium, and our self-constrained medium, the uniaxial strain case, the stress deviators have to basically balance the amount of expansion you would have gotten, and we dealt with that earlier. The lateral stresses must exactly equal the stress required to balance the lateral strains so that there are no lateral strains. And so you have the material squished in one dimension. Now, because there is a difference in stress between the longitudinal and the transverse directions, there is an inherent shear stress and also shear strain at the microscopic level that go along with this. Eventually, the stress overcomes the strength of the material. Basically, you strain the material to the point where the stress that the material can support is exceeded by the amount of stress that would need to support in order to maintain that strain. When that happens, the material shears to relieve stress. And here I'm not talking about, a shear fracture, say, in an MTS machine where you, say, take a piece of a cylinder of some material and press on it until it fractures. I'm talking about shear down at the microscopic level. Involves twinning and other things, but the atoms fundamentally rearrange themselves. Now, they may rearrange themselves into exactly the same symmetric situation, so that essentially all that's done is you've shrunk the distances between atoms, but they do rearrange. That's plastic failure. Now, the important thing to note is that the material may still be supporting some amount of deviatoric stress, but those deviatoric stresses are small compared to what they would have been if the material had not failed. At very high total stresses, think very high pressures, quite often the pressure is much greater than the deviatoric stresses. And in such situations, as you will find out next week, it's common to ignore deviatoric stresses. But in a material that has failed plastically, where if you try to apply more shear stress, the material just flows, then it's behaving like a fluid rather than a rigid solid. This condition translates to the shear modulus being equal to 0. In that case, the shear wave or transverse wave velocity would be 0. So there is no transverse wave. And the longitudinal sound speed becomes this quantity c, which is the square root of the bulk modulus divided by the density. That's a bulk wave. Bulk waves occur in fluids. They're really the only kind of body wave or interior wave that a fluid can support, but they also occur in solids that have failed plastically. Okay, I've talked about mostly isotropic materials. I should point out that if you take a material, and I think I left off a few terms in the example of the orthotropic solid here. If you take a material that has properties that depend on direction, then wave speeds, stresses, all those things will also depend on direction. And they're going to be, and the strains, the wave speeds and all are going to be related to the stresses by whatever set of elastic constants applies to that material. So, you know, in a orthorhombic solid where you have 3 orthogonal directions, but the properties are not equal in any of those directions, the wave speeds, longitudinal wave speeds or shear wave speeds, will be different propagating in those different directions, and the shear wave speeds themselves will be different for propagation in some direction depending on what direction the transverse motion of the atoms is in. You can't combine these things into some single constant times the volume strain in order to get a wave equation. Now, you still have pressure being related to the volume strain by the bulk modulus, but the bulk modulus in these materials you can't relate it to a longitudinal wave speed, except when the material has failed. The important point here is that anisotropic materials exist, and they will have wave speeds and properties that depend on the direction of wave propagation. Now, materials don't go on forever. Sooner or later, a wave hits something. Either it hits another material or it hits the edge of the material it's going through, and there's nothing beyond that. What happens to the atoms, to the wave? Say it hits a free, what we call a free boundary, where the last layer of atoms in the material is all there is. There's nothing beyond it. The wave can't just disappear. It's carrying energy. It's carrying momentum. It cannot just disappear. But at the same time, at that free surface, there's nothing beyond it. There can be no stress where there is no material. And so we have to think about, how does the material behave when it hits that boundary? Sort of the extreme opposite is, suppose that you could have the proverbial immovable object that something is up against. So the material is so rigid that it is incapable of moving as in response to a stress. What happens? We'll call that a perfectly rigid, or sometimes called a fixed boundary. There are 4 situations: longitudinal waves with a free or fixed boundary, and shear waves with a free or fixed boundary. Let's start with the longitudinal waves. I was going to put a movie in here, but I realized that because of time, this was going to be a long lecture anyway. I apologize for that. If you take let's say a wave that has compression to it, so it's squeezing atoms closer together, it's a longitudinal wave, and it is propagating in some direction, and it hits a free surface. What does it do? Well, let's think about things at the atomic level. That last atom, or last layer of atoms at the surface, is pushed on, if you will, by the atoms deeper down, because as they move, they change the potential well that the atom is sitting in. And so it moves. It moves out away from the material. Now, because it doesn't have any other atoms that it is going to push on, the potential well is only half as deep as it normally would have been if it were sitting next to atoms that are on beyond it. So it continues moving along, and of course, it influences the potential well that the atoms that are deeper in the material experience, and so they get accelerated in that same direction. It basically pulls the atoms along, and that disturbance propagates deeper and deeper into the material in the direction that the wave originally came from. That means that this compressional wave that hit the free surface is actually reflected as a tensional wave. In terms of stress, we can say that the stress in the reflected wave is the negative of the stress in the incident wave, the wave that originally came in and hit that surface. An important thing is to note when we're dealing with elastic waves, waves where the stresses are very, very small, where the strains are very, very small, is that the speed imparted to those surface atoms, remember I said that the potential well they sit in is only half as deep, ends up actually being twice the speed those atoms would have had if they were in the interior of the material. So what we say in this business is that the free surface velocity is twice the in-material velocity. Well, what about reflection from a rigid boundary? Now the atoms at the surface are stuck. They can't move. They're in a potential well, but one side of that potential well is an infinitely steep wall. Newton's third law still holds. They are going to push on that immovable object, and that's going to push right back. As a result, those atoms, if you will, rebound. Say it's a compressional wave. The atoms effectively bounce off the wall, if you will, and then they push on the atoms that are deeper in. Excuse me. And so, compressional wave hitting a rigid boundary results in a reflected wave that's also a compressional wave. So the reflected wave has a stress that is the same magnitude and sign as the incident wave. And if that wave happens to, say, be a step function, so that in front of the wave the stress is 0 and behind the wave the stress is 1, then behind the reflected wave the stress is 2 because it's on top of the stress created by the initial wave. What about shear waves? Okay, now at the surface, say a free surface, the atoms now are not forced out of the plane of the surface. They're forced sideways. Again, the potential wells that they feel are only half of what they would be if the materials were in the middle. So they continue moving past where they would stop. And as you might expect, they're going to be forcing the atoms deeper in to move that same direction. So that when the wave is reflected, the sense of motion, the direction of motion of the atoms in the reflected wave is the same as the motion of the atoms in the incident wave. So that's the opposite situation from a longitudinal wave. The reflected wave has the same sense of motion to the person standing there watching the wave, if you will, as the incident wave. Now, there are some niceties that because the wave is actually moving in the opposite direction, it's really the negative, but for our purposes, just realize that the motion, the sense of motion in the material is the same in both the incident and reflected waves when the wave reflects off a free surface. And without going into a big long discussion as to why, you can imagine that the reflection from a rigid boundary is going to be the opposite. So the sense of material motion is different in reflections involving shear waves and longitudinal waves. Okay, now, what about when you don't have either of those two extreme cases? You've got something like, you know, aluminum next to copper or rubber next to steel or whatever. What happens then? Well, you can't really rely on either of these two situations. The property that determines how a wave will be reflected, and it is also transmitted, which is an important thing, is something called the impedance. The impedance it's the ratio of proportionality between the change in stress and the change in material velocity caused by the wave. So remember our longitudinal wave, it's this delta sigma, because it can be a change in stress. Nobody said the original stress was 0 now, is equal to minus rho CL times U, where I have started to recycle symbols now. Instead of U dot, where U is displacement, I'm going to be calling velocity, material velocity U. I apologize for that. That's just the way life is in this business. So the impedance in this material is minus rho times CL. At an interface, there are two things that have to be equal. The stress, really the normal stress, should be continuous. Really, I'm going to mainly deal with normal stresses and longitudinal waves, plus the material velocity has to be continuous. And as I pointed out, this is going to always be the case in terms if we're dealing with motion normal to the interface. In the case of shear, these requirements only apply if the two materials can't slide past each other, and that's what's called a no-slip condition. So for a longitudinal wave, at the interface, the incident wave will be partially transmitted and partially reflected. Whether or not the resulting waves have a total stress amplitude that's higher or lower than the original wave that hit the interface, the incident wave, depends on the relative impedances of those two materials. For a longitudinal wave with impedance Z1 in the material that the wave is coming from, the final stress has to equal Z1 times U sub I, where U sub I is the material velocity due to that original incident stress minus delta U1, where that's the change in velocity in U1, has got to equal to the impedance in the receptor material, the material the wave is going to go into, times U1 plus or delta U1. Why is that? The reason for that negative sign is because in that material, the wave is going back the way it came, the reflected wave, whereas the incident wave, or whereas the transmitted wave is continuing on in the original direction. So that's why you have a negative on the left-hand side there. If the material has a higher impedance, then the value of delta U1 will be negative. So that in reality, the quantity on the left-hand side is actually going to be larger than it was, than the original stress. If the second material has a lower impedance, then delta U1 will be positive, and the total stress that results from the wave interaction with the interface is going to be lower than the original wave stress. Well, I've mentioned this primarily in terms of normal. So I really have been discussing waves propagating normal to the interface. What happens if that's not the case? The wave is coming in at some angle. In the case of longitudinal waves and one polarity of shear waves, you'll get both normal and transverse components of the material velocity relative to the interface. And that results in something called mode conversion. So if you have a pure longitudinal wave coming in, what happens is at the interface, the velocity components associated with the material motion have both transverse and normal components. And so you produce both normal and transverse waves in reflection and transmission. Unless, of course, the material that the wave is going through can't support shear stresses. It's a fluid. This is actually a common situation in seismology for those of you who are geophysics aficionados. Seismic body waves encountering a boundary in the Earth, because most of them come in at oblique angles, undergo mode conversion. And this is how we originally found out that the Earth has a solid inner core. The outer core is a fluid. It can't transmit shear waves, but based on travel times, we found that, or it was found, I didn't do it, it was found that the inner core, when it was hit by longitudinal waves in the outer core, produced both shear waves and longitudinal waves that then reemerged and underwent, in the case of the shear waves, underwent mode conversion to normal waves again, to longitudinal waves that allowed people to understand that the inner core actually could support shear stress and therefore was solid. Okay, so we've talked about very small changes, very small displacements, so that the elastic constants are assumed to be constant. However, if the amount of strain of a material is finite, then the restoring forces that give rise to the elastic constants and thus to the elastic constants themselves also can change. For example, let's take the bulk modulus. Remember I said bulk modulus is actually a thermodynamic quantity. The simplest version of an equation of state, or at least the compressional part of an equation of state, beyond just assuming that bulk modulus is constant, would look something like this. The bulk modulus is a constant plus some constant derivative with pressure times the pressure. Even for isotropic solids, all the elastic constants can change with changes in the strain state or stress state. So let's take a material that's a fluid. So Life is simple. The same applies even if it's a solid. But to make life simple, we'll talk about a fluid, so we don't have to worry about the shear part of the situation. Longitudinal, bulk, sound speed, and the materials given by this equation. Now you notice I put a subscript S on K. Processes in elastic waves and waves in general, except for a few special cases, are generally fast enough so that heat transport can be ignored. It's basically adiabatic. There is no heat transfer. And if the wave is elastic, this is also isotropic, so that we use something called the isotropic bulk modulus. There's another bulk modulus out there called isothermal bulk modulus. That's the bulk modulus that you would have dealt with when using the Helmholtz potential that Lauren dealt with last week. Now, let's take a wave that has some finite amplitude, and then let's make it a compressional wave and run it into the material. And it has a finite rise time, so it's a ramp. If you look at pressure or material velocity or anything like that, as the wave propagates there to the right, it undergoes an increase in any of those measures in the pressure. Let's call it pressure for now. And let's imagine, as we did with Lauren last week, that our ramp is actually a lot of little bitty steps, each one with a pressure increment delta P. Well, what happens then? Well, in that first wavelet, it raises the pressure slightly. That causes a slight change in the bulk modulus. Now, because bulk modulus has this relationship to the density, it changes the density too. And because the strain, remember this is a uniaxial strain, the longitudinal strain is also going to be the same as the density change, but in opposite direction. First, our wave speed is going to be this new value of C, which is related to the original value of C by this equation in the middle of the slide. And because the material has been foreshortened a little bit, it's compressed, the strain works out to where that wave in space now is moving faster than the original wave, so long as this inequality at the bottom of the page is met. That inequality is met anytime the pressure derivative of the bulk modulus is greater than 0. That's called normal compression. Almost all materials do that. A few things don't do that over some restricted range of conditions. Water ice at close to 0 degrees centigrade and at normal pressure is one of those weird materials that doesn't do that. But let's take this to its logical conclusion. Each little bit of the wave moves faster than the one before. So each little bit can catch up with all the bits that went before. And this wave, as it propagates, will steepen up until it becomes a single instantaneous jump. That's a shock wave. Now, in the real world, things are more complicated, but we'll leave the complications until next week. Well, what about decreasing pressure? Well, if you have a material that has normal compression behavior, normal compressibility behavior, the exact opposite happens. If you take a wave that is a drop in pressure and you run it through the material, it actually starts to spread out. But what about this anomalous compressibility? What if K prime is actually less than 0? Well, you can end up in a situation where a rarefaction shock, a shock wave with a negative pressure jump, forms. And at the same time, if you put in a shock wave that's a positive wave, it'll actually spread out. One of the important examples that has been used for many years in the dynamic compression community before the advent of some of the modern facilities that we have was fused silica, basically quartz that's been melted and turned into a glass. It turns out that fused silica has anomalous compressibility, and a common technique to generate a high amplitude in terms of pressure, we're talking several gigapascals, ramp wave, is to hit a piece of fused silica with an impactor, so create a shock wave in it, and then allow that shock wave to spread out as it goes through before putting it into whatever material we happen to be studying. So that's the end of what I'm going to talk about this week. Next week it'll be shock waves and some of the details of shock waves. But I got a couple of problems for you all to noodle over. The first one, I mentioned that when a longitudinal wave reflects from a free surface, the velocity of the free surface, or the atoms at the free surface, are going to be twice the in-material velocity imparted by the wave. See if you can show that this is the case based on the idea of impedance matching. That's a fairly straightforward thing. The second problem is a little, only slightly more involved. And it involves thinking about a very common tool in material strength studies called the Kolsky bar. It's also known as the split Hopkinson bar or split Hopkinson pressure bar. In this particular tool, you've got a long, thin rod, well, actually two rods, and you sandwich a sample between the ends of those two rods. The sample needs to be smaller than the rods in terms of lateral dimensions, so the sample isn't very wide. And you hit the end of one of those rods, called the incident or transmitted, or the incident rod, with a longitudinal wave that goes down the rod, and it hits the sample, and part of it's transmitted, part of it's reflected. There are some complications because, you know, the wave can bounce back and forth in the sample between the two rods that the wave is in between, the sample's in between. And these waves are measured typically by strain gauges that are attached to the two rods. Because the rods are long and thin, the wave, as it propagates, ends up with zero lateral stress. It's uniaxial stress. Now, the wave equation stuff that we've been doing dealt with uniaxial strain, body waves in materials. Now we're doing what's called a rod wave, or a long, thin wave. It's a uniaxial stress wave. Let's assume that the rods and the sample are isotropic. Well, first, give me the wave speed of that wave in the rod in terms of the Lemay's constants or the other constants that we dealt with. And then, based on that, and on, again, impedance matching, what relationships between the elastic constants of the rod and of the sample would result in there not actually being a reflection at the interface with the sample. So those are the two problems that I've got for you to chew on. We'll talk about them on Thursday.
Very good. Thank you very much, Bill, for this excellent lecture. We look forward to the review session on Thursday. If you don't mind, also, if you would send me a copy of your slides, then I would forward it to the group so that people can have copies of the homework problems as well as all the formulas and equations that you had in there so they can work on those problems.
Okay.
With that, I suggest let's open the floor to questions. If you have questions for Bill, please type them into the chat box. So I'm just going to read them out as they come out. So first one is from Emma Dickinson. She says, I was glad to see the tensor review because I'm studying Eshelby's method for my project right now. What is the effect of inhomogeneities in a material on wave motion? For example, spherical, needles, fibers, etc.
Well, they complicate it. Basically, an inhomogeneity is an interface, a material interface. You've got a change in the properties of materials, and so at that change in materials, the wave is going to do what waves do at interfaces according to impedance matching, because these inhomogeneities are typically small in lateral extent and probably have inclined boundaries to them. You may get mode conversion in these things. You get waves that effectively refract and reflect, and so the sort of gross effect of that is that you get scattering of the wave, and you get the wave spreading out in time.
Next question comes from Todd Wong. You said that the incident wave is partially reflected at interfaces. Does the material with small grains absorb the wave better than large grain materials? In other words, does grain size have any impact on the strength of material under compression waves?
To the extent that the grain size isn't so big that you can't treat the material as isotropic anymore, and assuming that the grains are bound well enough together that they don't really, they are well, and their interfaces are good with each other, the answer would be no, with some caveats. If you're down at the grain level, then then it doesn't matter that the grains are randomly oriented. You would still see some effects of anisotropy if the original grains are isotropic. If you're talking about at the bulk level, then that effect tends to wash out. There are situations where, especially when you're talking about material yielding, where the grain size does matter. And I didn't really get into that. That's a discussion that I suspect will be brought up later in the course that I didn't want to get into here. But basically, the longitudinal wave, the transmission of the wave and its reflection is, ideally speaking, only dependent on the relative impedances of the two materials at the at whatever length scale you're dealing with. If you have a sample that's only 3 grains, then you can't call it isotropic.
I have a quick question myself. So you gave us a lot of overview of some of the fundamental, elasticity theory that underpins stress waves. I wonder, would you recommend some references that people could look into, especially if they wanted to go into greater depth, for example, in anisotropic materials?
Actually, most of the best references, in my opinion, that are not too dense are, people's online lecture notes and such. Kolsky's book is very good, but you have to be a little careful because he uses symbols slightly differently from what I did. In fact, much of my discussion is actually based on Kolsky's book. But for instance, he, in the off-diagonal parts of the strain tensor, he uses a different quantity so that his off-diagonal parts are actually half epsilon because of the way he defines epsilon. Trying to think, if you really wanted to torture yourself, you could probably get Love's book on elasticity, but that's an extremely big tome to learn about this. Possibly one of the other cases that doesn't go into as much detail on some of the finer points would be something like Richard Feynman's lecture notes.
Great. Thank you very much for those suggestions. We have a question here from Yupeng Zhang. Could you please provide some comments on the inelastic waves, for example, viscoelastic?
Yes, so elastic waves, of course, are waves in which we are assuming that the elastic constants are not changing. In viscoelastic waves, you have a couple of things going on. First off, the elastic constants can be changing. Such waves are no longer small amplitude or infinitesimal waves. They're finite amplitude. So the elastic constants in the materials are changing. The material is by definition yielding. So in such situations, because you have viscosity, and viscosity is a rate dependent, provides a rate dependence for this, you're going to have a situation where the wave speed depends on the rate of strain, not just on the elastic properties of the material. And of course, that gives rise to dispersion. At any particular strain rate that has a viscosity associated with it, you can write similar equations of motion to the elastic equations of motion and solve the wave equation in the same way you would. But now that wave equation is going to have an answer, a velocity that has a rate dependence built into it.
Okay, are there any other questions at this time for Bill? If not, I would thank you all once again for attending. Bill, thank you for this lecture. We very much look forward to the review session after we've had a chance to look at the problems. We'll see you on Thursday, and as always, I will post a recording of this session as soon as I receive it. Thank you very much.
You're quite welcome.